can see that using, where did my link go? Page up, right over here. We use this program, and we filled in our reflect across the x-axis matrix. We filled in a matrix that represents the vertices of the quadrilateral. These are the x and y points, and the last row is just all ones. And the answer to it represents the x and y values of my reflected quadrilateral across the x-axis. Thank you, John. So now it says, all right, find the vertices of the figure, the original figure, after it has been rotated 90 degrees about vertex B. So let me come back up here and find vertex B for a moment. That is the location 4, 2. So I'm going to put this dot on here. We actually have to do a little thinking. This was point B, the location 4, 2. So they want it rotated 90 degrees, but they want it rotated about vertex B. We don't have a matrix that rotates about vertex B. We only have a matrix that rotates about what? The origin. We only have one that rotates about the origin. Let me see if I can find it here. Where were my rotation ones? There's my rotation ones, right here. Rotate 90 degrees, but it's about the origin. So what we are going to have to do to accomplish this is a 3-step process. We are going to have to move this point over and down so that we move it to the origin. Then we are going to rotate it 90 degrees because we have a matrix that does that. And then we need to move it up and to the right the same number of places that we moved it left and down. And that will accomplish this fact right over here. So if I am going to move it left, what is that, 1, 2, 3, 4, and down 1, 2, I need to do a translation matrix where I have moved it left 4 and down 2. 1, 1, 1, 0, 0, 0, 0. There is the translation matrix. Let's come right back over here. There it is, the translation matrix. So I'm using this matrix, to translate it over to the origin. Then, after we do that, that will be our step number 1. Then our step number 2 is going to be rotated. Number 1. Step number 2 is going to be rotated 90 degrees. Look at the book and tell me what that matrix is. 0, negative 1, 0, 1, 0, 0, 0, 0, 1. Then we rotate it 90 degrees, and then step number 3, we need to move it back to where it belongs, which means reverse this process. So we moved it left 4, and now need to move it back right 4. We moved it down 2, I need to move it up 2. 1, 0, 0, 1, 0, 0, 1. So let's see if we can't accomplish that. I'll find my, here it is. Find my program. So I have already, let me scroll up, I have already the original one. So there's my original coordinates. But I need to start with my translation matrix over here. So this needs to be a negative 4. And that needs to be a positive 1, and this is a negative 2, and that is a 1, so that all looks good. So my first step, I'll multiply these together, so multiplication. Now here's my answer. Now this answer, I want to insert back up in matrix B. So I'm just going to take this answer, well, where did it go? This one. Yeah, I want to take this answer, am I right? Yes. I want to take this answer and I want to insert it in B. So that negative 1, 4, 3, 0, there it is. It's in B. So now I'm ready to do step number 2, my rotation of 90 degrees. And you may have to help me. It was 0, negative 1, 0. And then what was it? 1, 0, 0. All right. So here's our rotation, so we will multiply it, and the answer to that multiplication right here, so there's my rotation. So now what do I want to do with this answer? Send it up to B, insert in B, so there it goes. And now I need to translate it back. So step number 3. See if I can remember this one. 1, 0, 4, 0, 1, 2. There we go. Then we translate it back. So I'll do that multiplication. And this should be the answer now to our final. Let's do a new one. To our final product, and we will see how good a job we did. So our new coordinates, if we did it all correctly, 1, 1, so I have a point right here, and 1, 6 over 1 up 6, and 4, 5 over 4 up 5, and 4, 2 over 4 up 2. Thank you. Over 4 up 2. Did we end up rotating that original? That's a long ways away. So let's get that. Did we end up rotating that original 90 degrees around point B? Now this rotation is a counterclockwise rotation. So here's this side, it should be up straight. Sure enough, there's that side, it went up straight. We rotated it 90 degrees around this point in that direction. Looks like we succeeded in it. So we can manipulate figures with these matrices. Next topic, that's topic number 1. Look in your book on page 559. That evidently comes from a movie that I've never watched. I don't know if any of you have ever seen that movie. I don't even know the name of that movie. Is that photograph there?
Good Will Hunting.
There you go. I knew it was a famous one. Never seen it, but maybe it's good, maybe it's bad. I have no idea.
It says it in the book.
What?
It says it in the book.
Oh, does it? Oh, okay. Says it in the book. There you go. Networks. We can use matrices to help work with networks. Now, what do we mean when we say networks? Well, coming to your mind may be computer networks. Yes, that can be. These points right here, the vertices, or sometimes they're called the nodes of it, they can represent Wi-Fi hotspots. They can represent computers on your network. They can represent your UPS driver, the points that you need to deliver to. So networks is a big topic that encompasses many things. These networks are called graphs, but they're not a graph like an X and Y graph. So these graphs are a set of points, the vertices, or those nodes. They're connected by lines, which might represent literally a network cable, or a Wi-Fi connection, or a road, whatever it happens to be. And those are called edges. So each of these are edges that are going along. And we often want to know, how can I go from one location to another location, and how many steps will it take to take that walk? We're going to get some exercise mentally. We're going to go for walks, and we're going to take steps. Well, I could go from 1 to 2, and then 2 to 3, and I have a 2-step walk going from 1 over to 3. Now, that's not the only way I could go from 1 to 3. I could go from 1 to 4 to 2 to 3. There are many different ways I could go. So there are many different walks that would accomplish, start at 1, end up at 3. So we are going to be, and let's see, the length of the walk, that's how many steps we have. So I think, there we go. Each thing that joins it, we have steps. A walk is a series of steps. The length of the length of this walk is a 2-step walk right over here. So what we can do is build what's called an adjacency matrix for any graph or for any network. And what it stands for are nodes 1, 2, 3, 4, 5, or vertices 1, 2, 3, 4, 5. They go both horizontally and vertically. And what these numbers are is how many steps there are, direct paths, edges, I guess I should say, between these vertices, between 1 and 1. If I start at 1 and stop at 1, there are 0 edges that go there. If I start at 1 and go to 2, 1 to 2, there is not a direct edge there, so that is why that one is 0. Start at 1 and go to 3. Start at 1 and go to 3. There is 1 edge. That's why that is 1, etc. 1 to 4, there's only one way. 1 edge. 1 step we're talking about. 1 way. And 1 to 5? 1 to 5, there is 1 way to do that one. Now all of these in this adjacency matrix are all 0s and 1s. And you just keep going across. 2 to 1, 2 to 2, 2 to 3, etc. until you fill this all up. The adjacency matrix will be the same order as the number of vertices or nodes that you have. So if I have 5 nodes, it's going to be a 5 by 5 matrix. Up here, if we were building the adjacency matrix, now I have 4 nodes, so if I did a 4 by 4 up here, and it's 1, 2, 3, 4 each way, 1, 2, 3, 4. 1 to 1 is 0. 1 to 2, there's 1 way. 1 to 3, that's a 0. There's not a direct edge. 1 to 4, there's 1. Now if I start at 2 and I say, okay, 2 back to 1, there's 1. 2 to 2, that's a 0. 2 to 3, that's a 2. There's your first example of something bigger. There's 2 direct paths. 1, 2 that I can get there. And then 2 to 4, 2 to 4, there's 1, etc. So that's called an adjacency matrix. So, what does that mean? Well, right down here says, figure out the number of walks of length 3. So, in an adjacency matrix, or in this thing here, how many different paths can we take, or walks, that will take 3 steps to get there? 3 steps to get there. In order to answer that question, we raise our matrix to the 3rd power. So I take my adjacency matrix and I cube it, and this will tell me the number of 3-step walks there are between any 2 locations. So let me just take this corner right up here, and let's see if we can figure it out. This is going from 1 back to 1. There are supposed to be 2 3-step walks. So look up here. I want to start at 1, and I want to stop at 1, and I want to take 3 steps to get there. Raise your hand and tell me one possible way. Josh?
4, 5, 1.
Going to go to 4, then I'm going to go to 5, then I'm going to go to 1. So there is one of those 2. 4 to 5 to 1. So I guess, there's my steps. I started at 1. 1, 2, 3 steps to get back there. Somebody else. There should be another one. They claim there are 2 of them. There should be another one that's exactly 3 steps long that starts at 1 and goes back to 1, but it's a different walk. There it is. 1 to 5 to 4 to 1. That's a different walk. Start at 1, go to 5, then go to 4, then go back to 1. There's our 1, 2, 3-step walks. So that is what this matrix will then tell us. So, using that same calculator, find the walks through a graph. So it says, consider this graph, find the adjacency matrix. So I'll do it over here. We'll find our adjacency matrix. You'll help me find this adjacency matrix of that thing right up here. So I need to, first of all, so I'll clean it. That'll do it all out. How big is this matrix going to be? This is going to be a 4 by 4, so there's my 4 by 4. So going from 1 to 1, what is my number?
0.
0. 1 to 2. 1 to 3.
1.
1 to 4.
1.
And then this would be 2 to 1 as I'm on the second row.
1 to
2 to 2? 2 to 3? 2 to 4? Then 3 to 1. Is that not correct? Oh, correct. That's why it's 0. So this would be 2 to 1. I have a way to do that, but that's the only direct path from 2, is 2 to 1. So now I'm 3 to 1 on the third row. 1, 3 to 2, 3 to 3, and 3 to 4. And then 4 to 1, 4 to 2, 4 to 3, 4 to 4. There it is. So there is my adjacency matrix for this graph. So I'll get that adjacency matrix here. Insert it in our work. There's our adjacency matrix for that graph. Find a cube and use it to determine the walks of length 3 that happen to be between vertex 2 and vertex 3. So what do I need to do to my lovely adjacency matrix down here?
Multiply by 3. No, multiply by itself 3 times.
Okay, I raise it to the third power, multiply it by itself 3 times. The nice thing is it says raise to the power of 3. So I will say raise it to the power of 3. Here it is. We'll grab that. We'll do our whole work here so we can see it all. And now we have to answer a question. They say, all right, and then determine the number of walks of length 3 that go between vertex 2 and vertex 3. What's the answer to that?
1.
1. Between 2 and 3. Now I could also say between 3 and 2. It is still 1. Row 2, column 3. Row 2, column 3. It's 1. There's exactly 1. So tell me, what is that one walk? The only way you can go in 3 steps between 2 and 3. It's not hard. Start at 2, go to where?
1.
Go to 1,
3. Go to 4.
go to 4, and then go to 3. Step 1, step 2, step 3, there it is. 3-step walk. It's the only way you can do a 3-step walk starting at 2 and going to 3. Right now, it's just fun and interesting because we like college algebra, but there actually are some very significant uses for it. This is a very interesting, to me at least, application of this. A local rental agency has offices in Tampa and St. Petersburg, Florida. To start with, the agency has 40% of its trailers in Tampa. The other 60% happen to be in St. Petersburg. So right down here is a matrix that represents that. Tampa trailers, 40% of them. St. Petersburg, 60% of them. 86% of the Tampa rentals get returned to the Tampa office, but the other 14% end up over in St. Petersburg. So here is our Tampa and St. Petersburg again. 86% of them return to Tampa, but 14% of them end up in St. Pete. 81% of the St. Petersburg rentals, so this is a T and an S, row as well, row. So if I have 81% end up in, well, I shouldn't have said it that way. Let me erase that. In St. Petersburg, there's 81% back in St. Petersburg, and 19% of them get returned back to the Tampa office. The owner of the agency has determined that after N weeks, the percent of the trailers that will be at the Tampa office T and the percent of the trailers that will be at the St. Pete office S can be found by this, where N represents the number of weeks. Now I want you to think of what is going on here. Rental car companies do this. If you have ever tried to rent cars between 2 locations, at different times the prices will be different, even if it's the same route and you're taking it for the same number of days. We do this all the time when we run down to Alexandria on the home leave route, and we rent a car in Alexandria to get back here, and then rent a car here to get back down there. The prices are different every single time. And the reason is they have different number of cars in those two locations, and they need to shuffle them. And so if you're taking it from where there are not enough cars to where there are too many cars, they're going to charge you more. Now, if it's too many cars to not enough cars, then they like that. They charge you less. So this has to be figured out. What's going to happen? Where are my cars all going to end up? Find the percent of trailers that will be in the Tampa office after 3 weeks, and then after 8 weeks. So we have our information. And I need my first matrix to represent the original. So I'm going down to the 2 by 2. All I fill in is my top part. 0.4, 0.6. And then my second matrix. How did my rows and columns get off? There we go. My second matrix represents where they go. I don't know if you have noticed, but we have done no math by hand. It's all understanding what's happening, how to use it, but all the calculations are going to be done with this matrix calculator. So I am supposed to take this number times this number raised to the third power to start with for 3 weeks. What do you do first, multiply or powers? Powers. So I need to come down here and raise this one to the third power. So I'm going to raise that one to the third power. Here it is. There probably is even a way to do decimals if you like those decimals. So I'm going to do decimals. We'll do decimals to 3 places. Let me do it again. Raise it to the third power. All right, so there's my decimal. Now I need to send this back to B. All right, they did like the fraction. And now I need to multiply these together. A times my B. And this should be my solution wherever it went. There we go. This should be my solution for the first part at least, and that's all we'll do together. I'll do it for fun in a minute because it's fun while you're working on your fun. So right down here is my 3-week solution. So this is telling me that after 3 weeks, I have 52% of my trailers are at the Tampa office and 48% of my trailers are at the St. Pete office where they have located. And you can run this for 8 weeks. You can run it for 52 weeks in the year. You can figure out what's going to happen. How many staff do I need at this office? How many staff at that office?
Okay, so how are we going to do our testing on this if it's all on the computer?
I'll probably figure out a way. That's a good question. Okay. All right. Some of you have graphic calculators. If you want to, I'll show you how to do it on graphic calculators.